WACV.
Hello everyone. Today we have with us Joseph. Joseph is a PhD student at IIT Hyderabad. He's curious about how we can build machine learning models, which can learn continuously as we humans do. And today we are going to discuss Joseph's work on C4 Synth, which is cross caption, cycle consistent text to image synthesis, which was accepted at WACV in 2019. Also, we would like to congratulate Joseph for his paper Meta Consolidation for Continual Learning, which was recently accepted at NeurIPS 2020. So we look forward to hear more from you, Joseph. Please continue.
Thank you so much. This is indeed a great honor to be here and like to present this specific research work where we kind of try to figure out whether we can generate some images just out of like text sentences and text descriptions about it. So this is a joint work with my lab mates Arghya and Shailaja and my professor Dr. Vineet Balasubramanian. Yeah, so just as I kind of mentioned in the before, like please bug me with questions and let's have an open discussion throughout the talk. I think that would really help.
We will interrupt you. If any question, we'll definitely interrupt. Please go.
Sure, great. Right. So, I mean, this talk is basically split into like 5 sections, but then you'll get to know that each of them are very crisp. So I kind of like use this as a very lean template onto which we can hold on. But like most of the discussions, I believe will happen outside this kind of the templates that we have. Let's get started. So the main idea over here is like, okay, we need to generate an image from its description. And there has been a lot of work around this for a while. There are a few works which actively work on this. I mean, which has kind of solved it, but not solved it, but then like to some extent in a very controlled setting, in a very controlled set of data sets, like they have quite good results. But one of the key thing that we noticed about all the works in the community is like, okay, text descriptions is very big, and at times it can get even very confusing too. At the same time, there can be a lot of extra captions and extra data that we can probably get regarding a same image. So for example, assume we have a painter, I mean a human painter who's trying to trying to draw some image of, let's say, a bird. I mean, just saying one line to him doesn't make like a huge impact. But then, like, if we give him a set of descriptions saying like, okay, there is a bird, like there's a beak. I mean, so the beak is so really long. At the same time, the tail is not that like long, and it's black in color. And so obviously, I mean, it gives a much more intuition about what's actually happening. And obviously, the painter might be able to draw a much more better image out of it. So this is a motivation for our work. Why don't we kind of use multiple textual descriptions about a single image? So that is what we kind of explored in this in this work. So this image that we see on the right was kind of generated by the model by consuming the captions on the left. So we can see that the captions read something like that about the yellow petals that are surrounding the yellow anther. And then it says like it's very thin, bright yellow petals that are folded in to create a round flower. So if we compare the first 2 captions, we can say that, okay, there are some complementary informations, like, it says like it's very thin. And the first one gives you information that, like you have an anther and you need to surround the flower on top of them and around that. So each of the caption has explicit different information. And what we try to find, try to kind of understand from this work is like, okay, let's have a model. Let's have a model that takes all these different views of a single image, and what will happen if we kind of generate an image out of multiple captions. So the key novelty that we are kind of introducing in this specific work is something that we call as cross caption cycle consistency. So over here, we have, so how familiar are the audience with CycleCAN kind of a technique? Where
I'm not too familiar with it, so you can just give a brief intro. It will be great.
Okay, great. So that I can.
Also, I had one more question. The color gradient was that not a feature that was included, or maybe it is not that important because in all the captions generated, you're not talking about the that color gradient from the center to the rim of the flower or the background. So that is of not importance to us, or how is that decision made?
Right. So intuitively, we are feeding all these inputs to our neural network, right? And it by itself is kind of deciding on what is important and what is not important, and what to give emphasis on and what not to give emphasis on. And this is trained on a huge data set too, so it is able to kind of capture the variety of different characteristics, and at the same time, even images are used for training, right? So I mean, it is seeing a lot of images while it's training. So I believe it is from there that it's trying to understand that there would be a gradient flow, and I mean, so on and so forth. And yes, this is a handpicked example. So I mean, there's a huge, I mean, like a set of examples that we kind of have.
And when you're trying to, what kind of score will you use here in this case?
So it's not a inception score. So inception score is kind of used to evaluate the quality of a generated image. So if needed, like we can get into the details sometime down the talk when we discuss the evaluation metric.
Yeah. Cycle GAN, yes. Please do.
Sure. Yeah. So there is this very typical, I mean, very impactful work known as Cycle GAN, which came out from Alexey Frost group in UC Berkeley. So this is essentially like, I'll just give an intuition about how it's actually done. So assume these are images in domain A, and these are images from, this is domain A and this is domain B. Okay, so the typical example in a cycle GAN, is like, assume domain A contains all horse images, and domain B contains all, let's say, zebra images. Okay, and so what we really want to find out is, like, given a horse, we need to create a zebra. So we need to stylize an image of a horse as a zebra. Okay, so this is image to image translation. So so this is just a very naive example, but a practical example would be like converting, or let's say autumn images into a sunny image, or converting an image from, let's say a Da Vinci into the style of some other great painter. So this is something known as unpaired image to image generation. So this is unpaired because we are not giving a pair of examples, saying let's say this is an image of zebra and this is the corresponding image of something else, for example a horse. So and practically that's not possible, because we cannot have an image of a zebra and the horse in the same pose and its orientations and so on and so forth. So it's unpaired because all we have is a pool of zebra images and a pool of horse images. And what we really want to find out is a function f that maps images of horses into zebra, and let's say g that maps zebra back to horses. Okay, so once we learn this, then given an image of a zebra, like we just use a function to pass it on to the other domain. So this is domain A and this is domain B. So domain A contains all set of examples of zebra, and this contains everything of the other domain. Now, what cycle consistency ensures is, like, assume we have a function that goes from here to here, and let's call it f. And there is another function that we are learning that goes from this domain to this domain, and let's call it g. Okay, and there is this data point here known as a, and there, which is like f is mapping it to another data point, let's say b over here. Now, what cycle consistency essentially tries to figure out is, like, assume we are using f to convert a into something in domain b. Okay, and if we are using the function g on this generated image from f of a, then this should essentially go back to the same image A. So this is the cycle consistency that we are talking about. And the same applies to, the mirror applies to G also. So we start with B, and like f of B will give you a representation or rather an image in the A space, and f of that will kind of transpose you or rather land you back into the domain B. So this is cycle consistency, and this has been really used in a lot of domains in computer vision after this paper just came out. So this is cycle consistency, and this statement like CycleGAN is the paper that kind of brought this thing out, and it's a really good paper, so must read, I would say.
Joseph, how is this different from the discriminator in regular GAN?
Right. So a discriminator in a regular GAN setting, it just tries to identify whether a generated image is a real or not. Right. So it just tries to try to find out whether an image that it gets, whether it's generated by a generator or is it from a natural sample, which is the real image. Yeah. So I think it's fundamentally different.
Got it. Thank you.
Yeah. Sure. So CycleGAN, that's about CycleGAN. So this basically cycles up between two domains as I just enforced. So I just showed up. So we have C4SYND, where we kind of have transitive cycling across multiple captions. This is essentially what we are doing. So we have a text domain T1. Okay, so you can assume that this is a caption C1. Okay, a caption T1. And from this text domain, we are jumping into the image domain, and we get a representation, or we get an image over here. A standard discriminative loss will ensure that this image over here should be as close as to the real image I. So that is the DL over here. Let's forget about that for a moment. But from text domain, we jumped into the image domain, and from the image domain, we are going back into the text domain using another function. So assume this is a function f, and we are learning another function g to map it back here. And now we have another loss, just as this image is being made as close as to the real image I, we have another loss over here, which makes sure whether the generated caption T is close to another second caption T2. Okay. And from T2, we again jump to the image domain using the same function. We end up in I2, going back into the text domain T3. And this cycles up to this point where from the T4, we go back to the image domain, and we go back into the text domain to generate T5 hat. And this is, in fact, we have this loss that makes sure that this is similar to the first text that we just gave by. So we have a transitive cycling over here between the three domains. And at the end, what we are essentially doing is, cycling back into the same original text that we started off with. So this is cycling, but this is not the CycleGAN kind of cycling between two images on two domains. This is also across two domains, but then this is all multiple data points across domains.
One question.
Sure.
All these text T1, T2, T3, T4, T5 are interrelated, and they are correct for the image. We already know that, right? Or we are trying to find it.
No, so all the T1, T2, T3, T4, and T5 are essentially the set of captions that we are giving as input to the model from which we are learning. So we know that all these 5 captions belong to the same image that we want to generate on.
Okay, right.
Sure.
Joseph, later will you show how you are proving cycle consistency works for this case? Later will you?
Yes, I think it's intuitive because we are starting from a data point, let's say T1, and we are cycling back to it.
Oh, okay. Right? Understood.
Yeah, because we are starting with T1, and we are the last caption that we are generating. We are pulling it back. This loss essentially ensures that it pulls it back to where it started on. So that is the cycling that we are talking about.
Understood.
So there's no discrimination, like T2 and T5 resemble T1 more closely, while T3 and T4 do not. Is it like that?
That's a very good question. Yeah, that's a very good question. So essentially your question would be, what about the ordering of these captions? So aren't they important, right?
Yes, that's what.
Right. So ordering is actually important. So we didn't, it's not very important in our experiments. What we found out is like we kind of switch between captions, and then, like we are getting close to a similar performance.
Okay.
Yeah, so this is the kind of the crux of this paper. At least at the intuitive level, the cycling that we have that is working across different domains, or rather across different data points in two different domains, which we call as cross-caption cycle consistency. So to materialize this, we have two set of architectures. Now the question is like, okay, why do you want to have two set of architectures? And I mean, we'll start off with one, and we'll find out why we essentially need two. So essentially, we will initially start off with a one-to-one mapping between what I just showed before in the slide, and like what can it map to in a neural network parlance. So this is what we call as the cascaded C4 synth. So I mean, this is very simple, but it's just look a bit geeky. But let's step into this very carefully, step by step, and let's try to understand and figure out what's actually happening. So initially, when we start off, we have text, right? We have captions. So each caption is denoted by TIs. So in a very high level, what we have is like we give the first caption over here. We generate an image over here, okay? And we generate a caption for the same image over here, right? Mm-hmm. And then what we do is like, with the generated image features, we again go ahead and generate a second image. At the same time, we'll be passing the second caption to it. Mm-hmm. Okay, so this is the second caption, and from the second caption, we would be generating the second image. Okay, in order to maintain consistency, the first caption that we generated, we make sure that it will be close to the second caption, which we are giving up over here. Mm-hmm. So this is how we map this, like the figure that you saw over here. This is just a one-to-one mapping from what we essentially have here to here. All right. I'll step into the details. I'll step into what exact components there are, but on a high level intuition, this is essentially what we have. We have the first caption over here. Yeah. Sorry, go ahead.
Now, it seems like there is a unique caption for each image. So won't it increase the overhead in the sense like you are saying that yellow flower, there is no generic caption. There is no just flower. It's always yellow flower. So won't it increase the overhead in your case? So you have 4 or 5 captions unique to only one image. So you can't reuse those captions anywhere else. So is that a problem or no?
So essentially what we have here is like we are distilling concepts from these multiple captions into the single image that we are trying to build up. So what we have here is like this image is in the experiments I will show how, but like it's just a one single like canvas, and then we are kind of putting up information from this multiple captions into the single, let's say, canvas, and building up a single image. So the final image that we actually get is from the final the function output that we have, which is I4. And essentially, we are kind of building up on the single. That is the reason why we are sharing this backbone. So it's accumulating the whatever good features that we want for a specific image. We are accumulating that, and then like building up the features so that the final image that we are generating from the final generator looks good.
Okay. Maybe it will be clear if you move
sure,
on.
And one more thing to add up, maybe it will improve the current discussion, is like how do you kind of encode this text is also quite important. So like even if it's like a yellow flower, like it's not like we're not giving yellow flower to a network, right? We are encoding it. So how we are kind of encoding it, that's also quite important.
Okay. Yeah. Please go ahead. Please.
Yeah. Sure. So, as we have this high-level intuition, let's step into the details. So this is the text that we have T1, and this is phi T1, which is I know, like an encoding of the text image. So, sorry, of the text, right? So, so we know that we are actually doing text to image synthesis. So it's quite obvious to find out. I mean, like to have some kind of a description, a textual description that aligns closely with the image features, right? So it's quite. I mean, like. It's quite obvious that, you know, like if we are generating a text feature, and if, I mean, we know that we are doing a text to image kind of a setting, and then like if we can generate a text caption that is quite close to an image caption, then that might help. Apparently there is one really good work known as structure joint embedding, which I mean, it's a work by Eni Bhagat. So I mean, she has a wonderful work where they learn some kind of such mapping where a text and image features are close by for later classes. So I mean, I'll just flip over to my paper so that I can explain the real function that, or the optimization that really solves it. So so let's assume that we have a data set, we have an image in the data set, that's V, and the T is one caption that is corresponding to V, and Y is the label corresponding to that that image. I mean, sorry, the image V. And we are essentially trying to learn a function FV and FT. So if you check here, FV essentially takes an image as the input, right? And FT takes an text as an input. And what we are essentially enforcing in this laws is, so this I mean, the delta signal symbol over here, this is just a standard, let's say, cross entropy laws that essentially measures the loss between the label Y and FV also returns back a label. So how much it closely aligns. Now for a single image, we pass this image into F and we get the label for that image F, and this loss basically ensures that it should be correct. Similarly, we have the second set where we have the set, I mean,
label or a caption, sorry.
Which
label or a caption.
Yeah, so V is an image and T is a caption.
Okay, thank you.
And Y is a label.
Got it.
Yeah, so I mean, so FT is another function that takes an text as input and essentially makes sure that the class of the text is similar to, you know, like the Y that we have. Now the question is, how do you kind of define these two functions, FT and FV? And this is how we do it. Now, I mean, theta is actually an embedding of V and phi is an embedding of T. And this is just cosine distance between them, right? So essentially what we are trying to find out is like, how do you find out, I mean, like I mean, as I just alluded before, this should actually return the label of the corresponding V. And that label is nothing but the argmax of all the kind of text that we have in this corpus that aligns with this image feature. Here we are kind of embedding, you know, how text and image should be similar to each other.
Got it.
And FT that we have over here, it essentially does the same, but the expectation is over, you know, like the images that we have, right? I think that's clear right now.
Yeah. So how is this label? Okay, the label is just how is it different from caption? Any distinction? Yeah.
Label from a caption, is it?
Yeah.
Right. Yes. So the caption is nothing but T.
Yeah. Caption. Yeah. It is straightforward. Yeah.
Right. So this is how it is. So I mean, if we kind of take the example that we just saw in the first slide of that bird is actually belonging to a specific class. I just forgot the class of what exactly the class of that bird is, but you know, like that I mean, the label that we have over here is nothing but the class of that.
Okay. So it just identifies the class for that image.
True.
Good. Yeah, thanks.
Yeah, yeah, sure. So this is how we kind of go about it. This is how we kind of have just a single function phi. So this phi is same as this phi. It's just like notational difference, but this phi is same as this phi. Okay.
Okay.
Sure. So this basically gives us, like an embedding for the entire caption. And from here, what we are essentially doing is, like there's something else known as conditional augmentation that was introduced in another related work known as StackGAN. So StackGAN, what essentially it tries to do is like, this is discrete, right? This is just a vector representation of the entire text. And now, we are introducing a conditional form version of the same. Essentially, what we do is like, we just have a very small neural network, a single layer network that takes this as input and predicts the mean and the covariance of a Gaussian. And essentially the T is sampled from the distribution. So this is conditional augmentation. This would be something like this, where like this mu and sigma that we have are essentially two neural networks with its own parameters that takes this encoded phi ti. So it takes this phi ti and then like it parameterizes. It takes a phi t as input, and it is used to predict back the mean and the covariance of a Gaussian, and ti is essentially sampled from that. So which is a very smooth distribution from which we can sample t. And with that, we end up with t tilde, which is essentially the vector representation of the caption that we have. And this is in fact appended to Z, which is nothing but the standard noise vector that we have in a generative adversarial network. So these two are appended together, and then it's just passed on to a backbone network. So this is just a standard neural network architecture where we are stacking up a few conv layers, and we essentially, when we reach here, we have a set of features with us, right? Now this set of features is given to a generator and is generating an image. This is compared to with the real image that we have, and this we have the standard discriminative loss over here.
So this is standard GAN architecture. This
is the standard GAN, yeah. The discriminator of the standard GAN is as such, and the features for the generator are picked up from this backbone that we have.
Got it.
And going forward, so the extra piece over here is like the same set of features that are given to the generator are given to this cross caption cycle consistency network, which is essentially an image to text synthesizer. So if you are aware of like the works like Chouette and Entel, where we are attending to specific areas inside the feature map, and we are generating an image, a text from that, right? So that is a standard kind of a setting that setting that we have for when generating text from an image. So we are piggybacking on that to generate this second T2, and we have a loss that ensures that T2 hat that is generated is close to T2. I think that's clear. So this just completes a single V1, like a single, like image generation and text generation. So if we go back to this architecture that we had, we went from T1 to I1 hat, right? And we have reached, from the features of I1 hat, we have reached to T2 hat. And we have the standard discriminative loss that ensures that, this generated image is close to the real image I.
Understood.
I think that's clear.
Yeah.
Having been here is just a recursion. I don't mean a recursion in like the same network being used over and over again, but then like intuitively what we are doing is like we are stacking up another set of layers into the backbone, which takes this backbone features that were generated by a B1 SBI, like this is like looping up over n-1, that is where I comes from. And this takes a second caption TI. And we are clubbing up the features over here. And yes, so we are again generating an image from there. we have the, generating another text description from here and so on and so forth. And so finally, for our loss to be cycled, we ensure that the last text that is compared against will go back to the first caption that we started off.
Got it.
So yeah, so this is the cascaded C4 synth. So if there are any questions, I'll be happy to take it right now.
So how did you use the data set, or is that coming up later? How you use the data?
Yeah, so we have used two data sets to experiment our work. One, which is the standard in the text to image community. It's one is one is the Oxford BERTS data set, and the others are FLAS data set. So I'll discuss those down the line.
See, I just wanted to know how it looks like, because I was not aware of those two data sets.
Sure, I'll get into that. So, one key problem that we can identify from here is, once we train this network, assume we are training it to assimilate information from 3 captions, let's say. We just cannot expand this to, let's say, to consuming 4 captions. So that's static. The number of captions that we are using is static to the network architecture that we have. So that is a problem with this network, and that is what kind of led up to the second way of doing it. We call it recurrent C4 synth. So essentially what we have is, like, we start off from a single a set of generators, discriminators, and the cross caption cycle consistent network. And this is essentially acting in something in a recurrent fashion, where at each time step it will be consuming a new caption, and then we will be doing this cycling over there. So the major difference over here that we have over here is that we have this hidden state, which is used to accumulate information from the generated image and the previous hidden state. So this helps us to keep track of the current state. In previous kind of setting, we had this backbone which was kind of expanding in order to keep that kind of information across the consuming different captions. So we have an initializer module here that initializes the hidden state, and from there it will consume the first caption. The generator is this good old generator that we saw before, and then it will generate an image where the image discriminator, the standard discriminator, tries to discriminate the image. We have the image features which are fed onto this cross caption cycle consistent network, which we saw before, and this is T2 going in. And what happens different from here is, like, in the second time step, we have the image going in, the generated image going in, and the hidden state, and this is updated. The hidden state is updated, and this just goes on. So we have a recurrence formulation over here, which is something like this, where at each step, the image is generated by the hidden state and the and the text description at that point I. And the hidden state is in fact a function of the previous hidden state and the previous image that was generated. I think that is clear. So
Yes.
this is a recurrent
Yes.
formulation.
Yes, it is understandable.
Sure. So these are data sets. This is Oxford FLARS data set and the Caltech BERTS data set. I'm sorry if I got wrong. Like, I think I told Oxford BERTS and Caltech FLARS before.
Yeah.
But yeah, so this is a data set that we have. So just a primer on the data set. So this data set is exclusively, or rather, like, it's really well used in the zero shot domain, where we are zero shot, few shot, one shot setting, where we have some we should kind of generate a new, or rather we should kind of classify new images with 0 labels, or 1 label, or a few labels. So the structure of the data set is pretty neat, where you have an image and you have corresponding captions of that image. And then we have a semantic, and we have the label for that image. And then we have a set of semantic attributes for that image. So semantic attributes is used for the shots, the few shot literature, But we here, I mean, and we are not using the semantic attributes that are there in the data set.
Why? Why is that so?
We just need, maybe just don't need that, right? Because like all we are relying on is the set of captions.
Right.
And yeah, I mean, whether we can use the semantic labeling in some form, maybe like we can explore it sometime later, but like for now, we just don't need, we just don't find the need to use that, and we're just ignoring it. And inception score is a scoring metric that is exclusively, I mean, like it's quite well used in all image generation kind of a setting, where I mean, where it's an unsupervised way, I would say, to kind of score the importance or the quality of the generated, the visual quality of an image. So what we have here is like we do, I mean, so we do compare against, so this, I mean, this is a 2019 Jan work. So essentially all the work has been done in 2018. So we compare with the then good method, CVPR 18 work, known as HTGAN. And StackGAN and StackGAN++ are very strong methods, and which does text-to image synthesis, right? And we are able to be comfortable in Oxford dataset. We are able to beat the other methods at the same time. The latest CVPR, then like it is, we are a tad below them in inception score, and yes, higher inception score means better. Yeah. So this is the qualitative result, and we have, like, these are all generated from our synthesizer.
Okay, since my knowledge of both the data sets is very less, can you also explain why did it happen that on CUB the model did not perform so well? Like it performed well, but as compared to HTGAN.
Right. There can be a couple of things, I would say. Maybe the bird descriptions that we had, maybe it didn't sound well, or is it maybe the kind of the even the methodology per se will not be as competent as maybe like the other method to kind of like be better than them. So I mean, like, yeah, I just don't have a very clear answer as to like why the numbers doesn't match up, or rather, I mean, be better than HTGAN. Yeah.
So is it usual that one particular model, say we introduce for anything, fits well to one set of data set and does not fit well to another data set, and like it cannot be generalized? Is it usual?
It may or may not. Like the specifics and the characteristics of the data set is completely different. So I mean, it's not. I mean, it's not very intuitive that one method should work for everything across the board. So yeah, it may or may not happen that we are good and better than the others in all data sets, or yeah.
So this comes under that non-explainability of AI part, maybe.
Yes. So yeah, maybe, yeah.
Joseph, okay. Yeah, I think you can go ahead, right?
Yeah, I mean, like I can pause. I mean, please go ahead.
Yeah, I just had a question about that hidden state. Do you talk about it later on, or
no, like if you had, I mean, like we will discuss it here, right?
Yeah. Maybe in the in the hidden state. How are you? I didn't understand. How are you updating?
Sure. Yeah. So the hidden state, essentially in our actual model implementation, what we have is like this an 8x8x8 cube that we have. So this 8x8x8 hidden features are kind of updated with reference to earlier generated image features, to be exact, right? And how this is kind of done is like the image features actually coming out over here are also 8x8x8, and the hidden state that we are designing over here is also an 8x8x8, and we are stacking this back to back and doing a 1x1 convolution across the board, and we are learning that weight also, and that is how the update module actually works out. So the input is it's two 8x8x8s, and the output is a single 8x8x8.
So without that state, what would happen? What is the result without the hidden?
Right. So without the hidden state, there is apparently no connection between the generated image, the previous generated image, and I mean, so the, we really essentially, I mean, lose the set of arrows if we don't have that hidden state to connect between them.
Okay. Okay. Thank you. Thank you very much.
Sure. Yes. So. Right. So these are some, qualitative results from our. I think this was on the cascaded C4 synth, and this is on the recurrent C4 synth. So yeah, all these are kind of generated from the set of captions. So note here is like the cascaded version. We just use 3 captions per each of, like for generating these images. I mean, we were limited by the number of, the amount of memory that we have on a GPU. So that is why because like we are stacking up a lot of features for, each stage is, we are building out, right? But a recurrent C4 synth doesn't have that problem because we're kind of, reusing the set of modules that we have, and we are actually backpropagating through time. Which is our standard recurrent kind of way of update. So yeah, so here we are using 5 captions. The reason why we're using 5 captions is like the data sets had 5 captions, so we're using 5 captions.
So Joseph, how do we interpret this? The first row is straightforward. You have caption matching image. Yeah. And how are the next 2 rows? How do we interpret that?
The next 2 rows is like I'm just not showing the set of captions that were used to generate those images. I'm just having a set of images that were generated from the flowers data set here, and this is from the birds data set.
Got it. Thank you.
Right. Yes. So interesting where we are. What we have is like a set of individual generations as we are kind of progressing up. So this is the output of the first stage, and this is the output of the second stage, and this is the output of the third stage, and the output of the fourth stage, where like we are consuming each different captions at each of the points. And this is the output from the recurrent C4 synth. So essentially we can see that the quality is improving, and then it is essentially building up a lot of semantic features as we go along. Right. So this image that we have over here is what we find out when we interpolate the Z. So if you remember, we had a Z when we started off here, right? The Z vector that we sampled from normal 0, 1 here, and the Z vector that we have here. So we what we have is like we kind of that in that latent space, we just kind of traverse that latent space and generate images. And this is the kind of images that we get when we move across that that latent manifold that is learned in Z. So what we see here is like different poses and angles of the same bird. So the bird essentially has this yellowish tinge, right? And that is consistent across all, and the brown feathers are also kind of consistent across each. But at the same time, these are different views of the same bird. So this is just another result that we have.
So the labeling for those images would be what? I'm just trying to wrap my head around. You are feeding captions to the model, and you're able to do the text to image mapping. True. So inherently, this data set for if I just went to this data set, what text would just correspond to any of the images? Just bird, yellow, what?
Yeah. So these are so I think this can probably answer your question where it's a caption of that is fed in.
Yeah. Thank you. Yes.
Yeah. Okay, I think there's a quick side note. So the original data set doesn't have the caption, so it was introduced in another work. The captions were added to the data set as another work. Yeah.
Okay.
Yeah. So yes, so these are some results that we have. So we heard all the good parts of the talk and the good parts of the text to image synthesis. Now, the bad part is like, okay, this works only in a very controlled setting. So there are works that have results on, I believe, our MS Coco, and it's really bad. It doesn't scale up to the real text to image, so it just cannot generalize well out of the box into other domains. So those are the downsides. But then this is not a downside of our work. This is the entire community is kind of striving to kind of leverage that. So I mean, I believe if you are interested into such, I mean, in this kind of technique, then that is something that like need to keep in mind. But and this is like a lot of papers are there in the space by good labs, and very good people are kind of investing time in this. So this is really interesting to work on. Yeah, but I mean, before I wrap up, I think I think I should point out to the negatives too. That is why I kind of alluded to that. But I mean, overall, I believe like, yeah, we had Cifosynth, we consume multiple captions, and then we have like two generative models for that, and then we had kind of good results on 2 data sets. And I mean, when in 2018, when we stopped this, we had this plan that like we need to attend to different parts of the caption differently. Like we need to incorporate attention into the model, and that can probably help the model to like fare well. Apparently in CVPR 18, there was a paper which was concurrent to our submission to WACWI, where they were using attention for text to image synthesis. So that is the work attention GAN that we have. So
yeah, you can pull that up.
Pull that up. I'm just doing it up. So this is attention GAN. So essentially what they have is like, let's see the result first. So because that helps us to get an intuition on what we are actually talking about. So on CUPS dataset, what we have is on, I mean, if you see this is stack GAN and this is stack GAN++, and the increments that we're talking about are in the order of 0.1, right? 0.6, 0.7, but attention GAN just came up and then like it's a 1 point improvement. So that's a huge thing. And as I just mentioned before, on harder data sets like MS Coco, it's really hard. For the other for the other methods, but attention GAN really pulls it off very well. I mean, but still, like if you see, these are the images generated by attention GAN. Also, it's not very realistic, but still it's much harder. I mean, much easier, much better than what we have on other baseline methods, and it's a much harder problem to solve because the variety in the images are really hard. So, so this is attention GAN that came along, and this is attending to different parts of the image, right? And this is the architecture that they have. So they have like, I mean, the caption coming in. We do have a text encoder. We have word features and sentence features. So in our C4 we just had a sentence feature. So they do have word features also. And
something
if
similar to
we
that,
had followed along, if we followed along C4 then like this is quite similar, where we have this, we append the textual features to noise vector and then feed into the backbone, and then we have a generator up here which generates an image, and then we do have a discriminator up here which does a discrimination. And the additional part over here is like it attends to the, instead of passing on the captions of the, I mean, maybe the same caption, in our case we had different captions, so instead of passing along the same caption features, we are attending to the different parts of the same caption using this F attention, right? And we are again building up the backbone, and again we have another generator that generates another image, and this just goes on and on. So the additional part is this caption, where at each stage we are attending to different parts of the word features over here. And finally, we have the final generated image. And what happens is like we do map it down into the feature space. So we have an image space over here and a word space over here, or the text space over here. And there's another layer of attention, deep attention multimodal similarity model that does, like a correlation between, like the features in the latent space. So this is attention GAN, and this kind of blew up the entire space of text to image in 2018, where this is a huge improvement over the baselines. And fast forward to 2020, I mean, like there is another work which has built upon both our work and the attention GAN. I think this just appeared in 2020 CVPR. So this is a work where so essentially, if we go to the architecture diagram, I think you might see some familiarity with the attention GAN that we just talked about, where you have text, you have sentence features over here, and you have word level features over here. So this is for this sentence feature embedding and word embedding. And essentially what we have here is the rest follows. It's the same. There's an additional module known as semantic. I just forgot the expansion for this, but it matches the the errors that are sampled using our conditional augmentation. That if you remember what we talked about a while before, the two feature vectors that we have for the text, there's a semantic SEAM module that transforms it to a single caption feature. And this is used by the generator, and it's discriminated, and then we have additional and function over here, which essentially adds up the attention part along with using multiple captions. So the gist is, high level, the gist is, this is attention using multiple captions. Right, and now this is the state of the art. So if we compare, again is 4.6, and this is we are at 4.07, and this is their method, which is up at 5.23. And C4synth, on Oxford also, this is how it is. So I believe this is one of the state-of-the-art methods that we have, and it's good to see that they just picked along the direction that we stopped. We were saying using attention might be helpful, and that is what we see in this specific work. Yeah, and they are not using cycle consistency or anything, but then our big picture was let's use multiple captions, and cycle consistency was one way that we kind of implemented our methodology.
Which paper is this, Joseph? The title? This is 2020 CVPR 2020.
Rich feature GAN.
Yes.
Oh, incredibly competitive, Joseph, this area.
Yes, this is in fact.
Yeah, you have to be almost because there is that lag also, right? You upload, then there's a review phase, so people are so
In 2017, there was a paper called Hierarchical Attention with Siamese Networks as the end. So from there on, I've seen this pattern of using a word level embedding, a sentence level embedding, and a document level embedding. All three of them separately into this.
Yeah.
Good. So in this, what are the contributions, Joseph? Major contributions here, apart from beating state of the art?
In this rich feature generation paper?
Yeah.
To be very honest, I don't know. I haven't read this thoroughly.
No problem. Okay. So what I was getting to it is, maybe is there an echo for you or no? Is the voice clear?
That's okay. I can hear. No problem.
Yeah. What I was telling is, when people are trying to build upon this, what motivation do they give, or how do they frame their problem? because you are, in your case, you have given some related work. When you were trying to go to your approach, you have given your related work. So in this case, when people are starting off with this text to image synthesis, what do they build upon? Basically, I'm asking what caveats are there to
Sure. Yeah,
pursue
I
that.
get
Yeah.
your question. So yeah, I get your question. So like, I think I can rephrase the question as to like, uh, what can be a key, a hole in the whole system that we can probably, like address, right?
Yes. Yes. Yes.
Yeah, that's a hard question to answer. There is no simple answer to that. But I believe so. If we see this specific CVPR 2020 paper, I think they gave much more emphasis to the text part. So if you see over here, like they have a caption matching, and then they have a refinement over the caption matching piece, and then they just build on top of attention GAN. So attention GAN, like it's sort of like people know that it works now. Like they're I mean, so but I would call it a bit incremental, but still, this is one way to do it. Yeah,
They can
and
use for feature engineering.
so. True, yeah. But but even when we started off, like we had this question, like why should we pursue, and this, and the reason why we thought like we can make a positive contribution to the entire community is like, okay, none of the works actually use multiple captions, and it was not very obvious why we should not use multiple captions. So that was what kind of motivated us to kind of pursue this.
Got it.